We may occasionally need to know when a graph is symmetric in some way, shape, or form. And you should know that graphs have lots of different symmetries, but there are really only three that I'm going to be talking to you about today and that are sort of important to us in calculus. The first is symmetric with respect to the x-axis, the next is symmetric with respect to the y-axis, and the last is symmetric with respect to the origin. The tests for these things are all pretty similar to one another, and so I figured I would just mention those to you now. So the first statement I have here is that a graph is symmetric with respect to the x-axis if replacing any y in the equation with negative y in the equation will result in an identical equation when simplified. So realistically, you're swapping y out for negative y and seeing if it leaves the equation unchanged. Similarly, if a graph is symmetric with respect to the y-axis, it means that when you replace x in the equation with negative x, the equation will again be identical when you simplify it. And the last one, the origin, the graph will be symmetric with respect to the origin if replacing both x and y with negative x and negative y will result in an identical equation. I do want to talk a little bit more about the last one because you may not remember what symmetry with respect to the origin actually looks like. Symmetric with respect to the x-axis sort of makes sense. If we take an equation like x equals y squared, which is a sideways parabola, this equation is symmetric with respect to the x-axis because you can see if we sort of flip this across the x-axis, you'd end up with the exact same shape. Right? Similarly, if you take y equals x squared, a parabola that you're probably more familiar with, this one is exactly the same if you flip it across the y-axis. Right. The one that people are generally not as comfortable with is origin symmetry. So origin symmetry, I've got an example of something here that has origin symmetry. The idea is if something has origin symmetry, it means if you take it and rotate it 180 degrees around the origin, you end up with the exact same graph, and I can actually show that to you. So if I take this graph here and I rotate it 180 degrees, so I sort of pick this thing up and spin it 180 degrees around the origin, you'll notice that the graph that I end up with, don't mind the fact that the numbers are upside down, notice that the graph that I ended up with is exactly the same as the graph that I started with. That's what it means when a function has origin symmetry. Okay. So you'll notice this last one had origin symmetry, but it did not have x-axis or y-axis symmetry. Okay. So I'll now ask this example. Determine the symmetries of the graph of this crazy thing, x cubed equals y cubed minus 2y. We have no idea what this looks like. So we're just going to sort of, wander into it and see what we can figure out. So let's first determine whether or not it has x-axis symmetry. Well, to do x-axis symmetry, we're supposed to replace y in the equation with negative y. When I do that, I end up with x cubed equals negative y cubed minus 2 negative y. And remember that if you have a negative thing raised to an odd power, it's going to stay negative. So this will become x cubed equals negative y cubed plus 2y. And the question is this equation here identical to what we started with? And the answer is no, not at all. In fact, this is actually quite the opposite. Right? So that's fine. This does not have x-axis symmetry. So x-axis symmetry, no. What about y-axis symmetry? And this, I suppose I'd like you to do this one on your own. It shouldn't be too difficult, but pause the video and try this out. For x-axis symmetry, replace x with negative x and see what effect it has on the equation. So that means I have negative x cubed equals y cubed minus 2y. Same deal as before. This becomes negative x cubed. And again, the question is this equation identical to the original? Once again, the answer is no. This does not have y-axis symmetry. Finally, we can consider origin symmetry. Okay. Again, I think you should pause the video and try this on your own. This now, for origin symmetry, we plug in negative x for x, we substitute in negative y for y, and we see what the effect is. So when I do both of those things, I'll have negative x cubed equals negative y cubed minus 2 negative y. Here I have negative x cubed minus y cubed plus 2y. And on the surface, this doesn't look the same as the original equation. But, oops, I forgot an equals in there. But if I were to multiply the whole equation through by -1, I'd end up with x cubed equals y cubed minus 2y. This is the same as the original equation, which means this does have origin symmetry. Okay? Now we may not know what the graph looks like, but we've determined it has origin symmetry, which means if you rotate it 180 degrees around the origin, you'd end up with the same graph, but it does not have x or y axis symmetry. In case you're interested, by the way, this is what the graph of x cubed equals y cubed minus 2y looks like. And you'll notice, just like we said, this does have origin symmetry, because I can take the graph and, rotate it 180 degrees and end up with the same thing. But you notice it doesn't have x-axis symmetry or y-axis symmetry. It's not the same above and below, or to the left and the right of the origin. By the way, as a final comment on this picture, you're not expected to know what this graph looks like. I didn't know what it looked like. I just threw it into my graphing program, and it showed me what this looked like. This is not something that I expect that you'll know, so please don't worry. This was just for illustrative purposes. So my last question, I'm making a little bit shorter by just asking about origin symmetry, but it's important that you guys know how negatives work with fractions. So I'd like you to pause the video, try this one on your own, see what you come up with, and then we'll discuss it. So to determine origin symmetry, we're supposed to substitute in negative y for y and negative x for x and see what we end up with. So we'll have here negative y equals negative x squared minus 4 over negative x cubed plus negative x. So I can simplify these things a little bit. I'll have negative y equals, now on the top, negative x squared is just going to be positive x squared minus 4 over, and on the bottom I can pull that negative out, and this becomes minus x. Once again, the question is this equation the same as this one? And we sort of look at it and say, well, the numerator is the same, but these all have negatives on them, and I think a lot of people's gut reaction is these are not the same because they're not exact opposites of one another. But I'd encourage you to think about how could you simplify this more. Specifically, what would it look like if you took this problem and multiplied both sides by -1? The left side is pretty clear. You multiply that by -1, you're just going to get y. But some people get sort of confused about, alright, so what happens on the right with the -1? And specifically, the question is, does it multiply to just the top, or just the bottom, or both? And to answer that question, you have to think about what -1 really means. Right? -1, when expressed as a fraction, would either be 1 over -1, or it would be -1 over 1. Specifically, what it's not is it's not -1 over -1. So when you're multiplying a -1 into a fraction, the one thing you can't do is you can't do this. You can't multiply both top and bottom by -1. Right? That would actually be multiplying by +1. Right? So what we do is you pick one of these. You either multiply the negative to the top or the bottom, but not both. So I'm going to choose to multiply it to the bottom. When I do that, I'll end up with x squared minus 4 on the top, and on the bottom, x cubed plus x. At this point, this equation is identical to the original one, which means yes, it does have origin symmetry.